Okay, so this right here is the famous Basel problem, which I've already covered once on this channel in the previous video. But this right here, it actually has a lot of different solutions. So this time I want to cover another solution, and this time we're going to be using differentiation under the integral sign. And this solution right here actually starts from a place that's very seemingly different from what we're trying to get to, but just stick with me here. So we want to take a look at this integral right here. Integral from 0 to infinity of the natural logarithm of 1 minus 2 e to the negative x plus e to the negative 2x dx. Now, you can immediately see that this is factorable on the inside, so if we just go ahead and do that, because this is a perfect square trinomial in terms of e to the negative x, this just gives us 1 minus e to the negative x squared. And then, because we have the power inside of the argument of a logarithm, we can take that down to the side. So now we get 2 times everything. So 2 times the integral from 0 to infinity of the natural log of 1 minus e to the negative x dx. Okay, so that first few simplifications were relatively easy. Now, from here, it looks like you're kind of stuck. But maybe we can use the power series for the natural log to help us out here. Now, let's derive that really quickly because I feel like it's easier to do it that way. Let's start off with 1 over 1 minus x. This is famously the geometric infinite series right here. The infinite sum from n is equal to 0 to infinity of x to the n. Yeah. So this right here is true. Now, if we go ahead and integrate both sides with respect to x, on the left-hand side, we get the negative natural log of 1 minus x, right? And then on the right-hand side, we get, the integral of a sum. If the sum is a power series, then we can interchange it, right? So now the integral goes on the inside. The integral of x to the n is just, here, let me write this out. Integral of x to the n is just 1 over n plus 1 times x to the n plus 1. Okay, now you see that this natural logarithm is already equal to this power series. If we just move this negative to the other side, then there you go. This is the power series for the natural log of 1 minus x, right? And of course, when you're integrating, you do have a plus c. However, if you plug in some numbers here, this c eventually comes out to just be 0. So it actually doesn't need to be there. So yeah, pretty cool. So let's use this right here on this. Okay, how do we do that? Well, you see right here where there's a minus x here, there's a minus e to the negative x there. So we just go ahead and replace this x with e to the negative x. So this 2 on the outside is going to stay. This integral bar is going to stay. Now, the natural log right here, we got to replace it with this thing. So we have the negative summation from n is equal to 0 to infinity of 1 over n plus 1. Now, down here we have an x, but up here we have an e to the negative x. So I'm going to go ahead and replace this with e to the negative x, as I said earlier. So we have e to the negative x to the power of n plus 1. But if we have a power to a power, the powers multiply. So x times n plus 1. And then dx. All right, so that's that. And yes, it still seems pretty weird. Why are we dealing with integral and e to the negative x when we're trying to find the sum of 1 over n squared? But I mean, at least we have the sum pulled out right now. One more thing here, you can notice that all the n's are in terms of n plus 1. So in reality, here you start, the first term is just a 1. Here, the first term is just a 1, because you start at n is equal to 0. Here, 0 plus 1 is 1. Here, 0 plus 1 is 1. So here you start at 1, then go to 2, then go to 3. So this 0 doesn't need to be there. It could just be a 1, and instead of n plus 1 here, we can just start with a normal n. And additionally, I'm going to take this negative outside. So we have a negative 2, right? And remember, this in here is a power series. So we can go ahead and once again change the integral and the sum like we did earlier when we were deriving this guy. So take the sum to the outside, but this time we start with 1, right? So that way, instead of n plus 1 here, we can just put n down. And then the integral goes on the inside now. Okay, on the inside, 1 over n e to the negative n times x dx. Also notice right here, this is also a constant, so let's go ahead and move that outside. Well, move it right here. So negative 2 times the sum from n is equal to 1 to infinity of 1 over n. And then let's just go ahead and integrate this guy, right? Just e to the negative nx. If you do a quick u substitution, you have to divide by this negative n, which is a constant, right? So here, first you have to divide by negative n. And right now we're integrating, right? So if you do a u substitution, that's what it tells you to do. And then you have the exponential, which repeats. So e to the negative nx again. Now, don't forget we have bounds from 0 to infinity. Okay, and we can just go ahead and plug it in. Right here, this should be multiplication. Okay. Negative 2 sum from n is equal to 1 to infinity. This right here, I'm actually going to multiply these to give us a negative 1 over n squared. So now you can see that it's finally popping out, even though we have a 2 here and a negative signs. Well, the double negatives actually will cancel out, so we'll do that really quickly. But anyways, now we have to evaluate this guy right here on these bounds, because, you know, this right here is where the x's are, and these bounds are in terms of x. Alright, so let's plug in infinity. Plugging in infinity to the top here, as long as n is positive, then the exponent becomes negative infinity, right? Because, yeah, this is positive infinity, this n is positive, positive times positive is still positive, times the negative, that's negative, so negative infinity. So, you remember that, but that's under the condition that n is positive, and n is indeed positive here, because it's indexing between 1 and infinity, so it never is negative. But if it was negative, then this right here would diverge. But it converges, because e to the negative infinity, it approaches 0. If you take a look at the graph of e to the negative x, as you go towards infinity, this gets closer and closer to your x-axis. So that means eventually approaches 0. Okay, subtract off. Now we plug in 0. E to the negatives, anything times 0, it's just e to the 0, it's just 1. Okay, so now we have negative 1 times all of that. I'm going to move this negative 1 outside, like this. So now it's just negative 2 times the sum from n is equal to 1 to infinity of 1 over n squared. Alright, so that was pretty quick. We've got to this result. Alright, so now we see that this guy right here is just negative 2 times of what we're trying to get. So, in fact, I'm going to put this up there, and then maybe we can find some other ways to manipulate this guy right here to help us find what that is. So, this is equal to negative 2 times the summation from n is equal to 1 to infinity of 1 over n squared. Okay. Okay, earlier I already mentioned that the technique we're going to be capitalizing on today is known as Leibniz rule for integration. So, this is the part where it gets kind of clunky and it's going to take a while, so just stick with me here. This is going to require a lot of patience. Okay, but let's use it, right? We got to set a parameter first. So, let's rename this function right here as a function of t. But now we gotta plant a t somewhere inside of this function right here. So where do we do it? Well, this negative 2 right here is kind of begging for us to replace it with the t, right? Because it's just a negative 2. Usually we expect, constant factors of 1 or negative 1. If we can make that our t, maybe it'll work out for us. So the natural log of 1, negative 2, we're going to replace with just t. E to the negative x plus e to the negative 2x dx. Now, if you've never seen this technique before, just stick with me. The point of this technique is to find I of t in a different form. Just put this guy in a different form. Not this integral, because this integral is kind of clunky to deal with right now. If we can put this guy in a different form, then we can just evaluate I of negative 2, right? Because if you plug in a negative 2 here, then you go back to your original. So I of negative 2 is just that guy right here. So I'm going to also write that down. T is equal to negative 2, of course, and I think that's an important distinction to make. Alright, so, and usually the way we put this guy into a different form is by differentiating both sides with respect to t, not x, t, right? So on the left-hand side, the derivative of I of t with respect to t is just d over dt I of t. There's not much we can do with that. However, on the right-hand side, when we take the derivative of this integral, we can actually interchange the order, right? And that is why this is so useful. That's called the Leibniz rule for integration, which is exactly what we're using. Except for one small minor caveat that really doesn't change much, and that is that this differential operator right here, d over dt, actually becomes a partial differential operator, because within this integral, you're now dealing with two variables, and you want to make sure that the t you're differentiating with respect to is independent from the x that's also mingling inside of here. So now you're partially differentiating this natural log expression with respect to t. Okay, so how do we do that? Well, we see in here that we're differentiating a natural log. So the derivative of a natural log is just 1 over the argument, and then chain rule if necessary. So 1 over the argument. The argument is just 1 plus t e to the negative x plus e to the negative 2x. Okay, chain rule, because there is another inside function within the natural log, right? So now we have to take the derivative of just this part by itself. Now 1 with respect to t, that goes to 0. Same thing with e to the negative 2x, because it doesn't have a t inside of it, so it's basically constant to us. So now we're only just looking at the middle term. The derivative of t times anything is just that thing itself. So in our case, that would just be the e to the negative x. So we're multiplying on a e to the negative x, which I'll just write up here in the numerator because it's the same effect. Dx. All right. Now what? So we did the differentiation. Now we notice that all of our all of our x's are trapped inside of these e to the negative x bundles, right? So maybe if we made a substitution, it would work out for us. Maybe let u equal to e to the negative x. Well, let's try it. Let's differentiating both sides implicitly. The left side you get du, the right side, the derivative e to the negative x is just negative e to the negative x times dx. Now here notice that we do indeed have an e to the negative x dx here. So if we just isolate that, divide both sides by a negative, then yeah, we have that negative du is that. Okay, so let's go ahead and plug everything in. But we still have the bounds to deal with. So, as I always say, these bounds are in terms of x, right? We want them in terms of u. And here we have a relationship between x and u. So, to get these guys in terms of u, we had just plug it into this, right? So for the lower bound, let's start with that. If x is equal to 0, e to the negative 0 is just u. E to the negative 0 is just 1, so u for the lower bound is 1. Same deal with the upper bound, except now x approaches infinity. E to the negative infinity, we already saw this earlier, it goes to 0. So therefore, if x is infinity, then u is 0. All right, now we can go ahead and deal with the inside. So let's write down the denominator first. The 1 is still going to stay, plus t is going to stay. E to the negative x, we said was going to be u. And then e to the negative 2x. That's just e to the negative x squared, right? And e to the negative x is just u. So it becomes u squared. Okay, next up. Up top, we saw that e to the negative x dx is just negative du. So we can actually use, you see these bounds, they look kind of weird because you're integrating from a greater bound to a less bound. We can actually use a negative sign to flip the order of those guys. So, what we get is, instead of from 1 to 0, we now have from 0 to 1, which is much better. And then everything on the inside is going to stay the same. Okay, so that's cool. now what are we dealing with? We have a quadratic in the denominator, right? And the way we typically deal with that is by completing the square. So let's do that with this right here. Okay, if we complete the square for this guy, what do we get? Well, to complete the square, there is a value that we need to add and subtract. And what is that value? It's just taking the coefficient of your linear term, so just the t, squaring it and then dividing it by 4. So you need to add t squared over 4. And why is that? It's because if you add it right here, then you see that these three terms form a perfect square trinomial, and you're able to factor it, right? Okay, so how do we introduce this plus t squared over 4? Well, we want to keep everything the same, right? So if we add t squared over 4, then we have to subtract t squared over 4. Because they cancel each other out, and everything ends up being the same as before. So we have to do 1 minus t squared over 4 plus t squared over 4. And then the rest of the stuff in the bottom. Yeah, okay, so you see that now here we have the perfect square trinomial, but because these guys cancel out, we basically just have what we had before, right? But now we can complete the square. So the integral bar is going to stay the same. Whatever's on the left side, I'm going to keep that there for now. But we're going to complete the square. And completing the square for this guy, you get u plus t over 2 squared. And then up top, you still have du. Okay, so now we have something squared plus a constant, right? Because right now we're working with respect to u, and this is a constant with respect to u. So let me bring back a formula that we were all taught in calculus 2 probably. And that is that the integral of 1 over a squared plus x squared dx is just 1 over a times the arctangent of x over a. And then, of course, we have a plus c, but for now, let's just deal with this function part. Okay, so see here that we almost have that form, right? Believe it or not, it actually is closer than you'd expect because we have this variable squared already. The only thing that's missing is a u substitution. It's just another substitution, right? If this guy became one variable, then we already have this x squared part. Now we just need to pull out this other constant squared. So we can deal with making this a single variable later by using a substitution. For now, I want to deal with making this guy something squared. And that's pretty easy, right? Because if you want to write it as something squared, then what cancels out with the square to make the original? It's just a square root. So right here, let's do this. Square root of, what do you have on the inside? And then squared, right? So that way, the square and the square root cancel out, and you get what you had before. But the reason why we're doing this, once again, is because we're trying to use this formula right here, which requires a constant squared. And this right here is our constant, the square root of 1 minus t squared over 4. So it's starting to look a little bit messy, but I mean, at least we're going to be able to integrate this in a second. All right, next, we need to make this u substitution. This whole thing needs to become a single variable. So, you know what? Here, I'm going to write down that these are actually in terms of u, because I am too lazy to come up with new upper and lower bounds. Okay? So, let's use w, say. Let w equal to this thing in here, right? Because we're trying to shrink this down into just one variable so we can integrate this. So that would just be u plus t over 2. And now you guys may point out that this isn't really necessary because this right here is linear, and with the linear term having a coefficient of 1. So having a u substitution won't do anything, right? But for now, I want to do it for the sake of completeness. Now, if we differentiate both sides right here, the w differentiating that get a dw, and on the right side, differentiating this gets you a du, because this t over 2 right here is just a constant, right? Because we're working in terms of u and w right now. So over here, u plus t over 2, we saw earlier, we set it to be w. So now this is now w squared. And up top, instead of a du, we saw that that's equal to dw, so we can just integrate with respect to with respect to w. Okay, so I'm going to move this up top, and then, yeah. Okay, so I did a few things. I got rid of all this work, and I rewrote the thing we had up here, because we saw that everything we had was just equal to each other. So therefore, this is equal to that, you know? And also a couple more important things. The formula that we're going to use, and then the substitution. And this is important to keep in mind, because we're going to be, after integrating this, bringing this back to the u world. So it's kind of important to see the relationship between w and u still, because these bounds are also in terms of u, but the integral is in terms of w. So yeah, it's a mess, but now we see that we do have the sum of squares form in the denominator, right? A squared plus x squared. That's that. So now we can take advantage of this formula right here. So we have the first term is the factor on the outside 1 over a. So 1 over a, which is the square root here, 1 minus t squared over 4. Next we have the arctangent of x over a, and x in our case is just w over a, which is the square root guy. So 1 minus t squared over 4. Now, really quickly, now also remember we have these bounds going from 0 to 1, sorry. But we saw that these are in terms of u. So if we want to plug in these bounds, we can't plug it straight into w, right? This is u is equal to 0 and u is equal to 1, not w is equal to 0, right? Or w is equal to 1. So we need to rewrite this guy in terms of u. So that's why I kept this here, because w is just u plus t over 2. All right. So we're done with that. I'm going to go ahead and erase this now. I don't know, you might need the arctangent thing later, but for now it's just this. Alright, so first of all, notice that this boy right here is just a constant. So if we're evaluating bounds, this is what we need to deal with, right? Because the u is inside of the inverse tangent. This right here, we can just factor out of the terms. So I'm going to keep this guy on the outside right here for us to deal with later. Alright, next, we got to start plugging in bounds. So, plug in the upper bound first. That gives you the inverse tangent of 1 plus t over 2 over square root of 1 minus t squared over 4. Okay, next, we subtract off plugging in the lower bound. So, plugging in the lower bound, we get the inverse tangent of 0 plus t over 2 is just t over 2, so nothing changes. I'm going to write this in black, sorry. It's t over 2 all over the square root guy. Square root of 1 minus t squared over 4. Close this parentheses. So this is what we have now. But I feel like there's a lot of simplification that can be done here, right? Say, for example, this guy right here. If we multiplied a 2 on the top and the bottom, then what do you get? On top, you just get a 2. But on the bottom, I want to drag this 2 inside the square root here. So to do that, we have to write it in terms of the square root. So 2, if you recall, is just a square root of 4, right? So you have a square root of 4 times this stuff that's going on inside the square root. This 4 just distributes into the 1 and then into the negative t squared over 4. So what you actually end up getting here is 2 over square root of 4 distributed into the 1, that gives you 4. And then this 4 right here cancels out with this 4 in the bottom. So this first guy is really just equal to 4 minus t squared, right? So I'm going to write this down here. And then we can do similar simplification to the rest of these guys. Because notice that if we multiply a 2 on the top and the bottom of this one, that'll cancel with this 2 in the numerator. And it'll give us this nice denominator that we found earlier. Same deal with this one, right? So yeah. Let's put down the first term. That would give you 4 minus t squared. And then we have the 2 arctangent functions that are subtracting from one another. Okay, so this right here, I'm going to keep it in parentheses. Remember what we said earlier? Multiply 2 on both the top and the bottom, right? So distributing that in, we get 2 plus t, because in the second term, the 2 and the 2 cancel. And in the bottom, same deal, right? Earlier we saw that 2 times this guy is just going to give us the square root of 4 minus t squared. So yeah, let's put that down. And then same deal for the second term, except we don't have this 1 to deal with. So it's just distributing the 2 into the t over 2, which just gives you t. So in this second term right here, the numerator is more simple. It's just the t by itself. And then the denominator, same deal. We're going to get the square root of 4 minus t squared. Okay, so this is already looking much better than this, that, even this right here. Okay, but now we have 2 inverse tangents. So how are we going to deal with this? Because, I don't want to deal with 2 separate inverse tangents. Maybe we can combine them, right? And if you recall, there is the arctangent addition or subtraction formula. First of all, arctangent, this is an odd function, right? So I'm going to take this negative and just plunk it in here and make this guy on the outside a positive, right? Because that's a property of odd functions. F of negative x should be equal to negative f of x. So right here, if you call this guy f of negative x, right, because you have a negative times your variable here, then you can also see that you can just go ahead and take the negative to the outside, which is what we had earlier. Okay. So now what? We have the arctangent addition formula. We can use that here. But it's kind of rare to have it memorized, off the top of your mind, unless you're in like a pre-calculus class. So I'm going to go ahead and rederive it here. All right. So let's have 2 angles, alpha and beta, right? Let's start with the tangent double angle. Sorry, not double angle, tangent angle sum. Because this one, more people will recognize as tangent of alpha plus tangent of beta over 1 minus tangent of alpha times tangent of beta. Okay, well, alpha and beta are just 2 angles, right? So alpha, let's rewrite as the inverse tangent of x, because inverse trig functions, they take in a number and they output an angle. They take in a ratio and then they output an angle. So let's replace alpha with inverse tangent of x, right? And that's where our inverse tangents are at the very end, they're going to pop out. And then let's call beta inverse tangent of y, right? Okay, so what does this give us? Up here, we still have this tangent on the outside, but now each of these guys on the inside, we're going to replace with what we set them to, right? So alpha is just inverse tangent of x, and then beta is just inverse tangent of y. Okay, so what about the right-hand side? Well, see that tangent of alpha is just tangent of inverse tangent of x. There's a tangent of an inverse tangent. They're going to cancel and leave you with just an x. Okay, same deal with the tangent beta. Tangent of beta is just tangent of the inverse tangent of y. So the tangent of the inverse, they're going to cancel and they're going to leave you with whatever's on the inside, and that's just the y. And the bottom, same deal, right? You have the 1 minus, that's going to stay. Tangent alpha, earlier we saw that was just x. And then the tangent beta, we saw it was just y. So we're almost there. And you can see that the reason why we did that was A, the right-hand side is now simpler, and B, we have this inverse tangent plus inverse tangent form that we're looking for to be able to simplify this guy up here. All right, so one last move. If we just go ahead and take the inverse tangent on both sides, this guy on the outside right here is going to disappear. And that's going to just leave us with the inverse tangents that are on the inside. So inverse tangent of x plus the inverse tangent of y. Now earlier, remember, we had to take inverse tangent on both sides to get rid of this. So now there's an inverse tangent on the outside of this. So this should just be the inverse tangent of x plus y over 1 minus xy. There we go. So this is what we were looking for, right? And all we can derive this straight from the tangent angle sum. So yeah, let's go ahead and apply it now. Okay, so first of all, notice that the sum is inside of here. So this guy on the outside is still not going to be affected. It's just going to sit out here, right? So square root of 4 minus t squared underneath the 2. Okay, but now we can combine these guys. So these 2 inverse tangents just become 1 inverse tangent by itself. On top, we have x plus y, right? So it's going to be 2 plus t over square root of 4 minus t squared. That's our x. And then add it to the y. So the y is just negative t over the square root of 4 minus t squared. Notice that this negative can actually just come down to the side here. And yeah. All right, time for the denominator. 1 minus x, which is, once again, this, times y, which is that. Okay, and same thing with the bottom. Notice that this negative and this negative, that makes a double negative. They cancel out to just make a plus. So we're going to write it like that. Okay, so there we go. We've used that. Now we don't need it anymore. Yeah, but we're still going to actually use the tangent angle sum later. Well, you'll see. This is a very intricate thing. Okay, so now we have this, but we want to simplify the inside just a little bit more because, you know, currently we have a bunch of complex fractions and it's not very fun. So no, let's take a look at the denominator first. The denominator, you see how we have this guy, these two square roots multiplying? Well, this times that, if they're the same thing, it's just one of them squared, right? This times that is just square root of 4 minus t squared squared, and that's going to cancel with the square root. That's just a very, you know, long-ass way of saying this guy right here, the square root and the square root, they're going to cancel after that you multiply two of them together to give you whatever's on the inside, which is 4 minus t squared. And on top, you have 2 plus t times t. The t is going to distribute in. It's going to give you t squared plus 2t. Okay. Okay, and on the top right here, so this is going to be the denominator. Let's work on the numerator just a little bit. See that they have the same denominator. That means we can combine the two. So we have 2 plus t minus t, over the common denominator, which is 4 minus t squared. The plus t and the minus t are going to cancel, so the numerator is just going to leave you with 2 over that guy. All right, so now we can get ready to simplify the complex fraction because this right here is already more or less the form that we can work with. All right, I'm going to move this up here. We still have this constant guy. It's the 2 over square root of 4 minus t squared. All right, on the inside, well, we still have this inverse tangent, right? But now on the inside, we can multiply by the least common denominator. And out of 4 minus t squared and square root of 4 minus t squared, it's just the 4 minus t squared, right? And I'll show you how we break that down for this, but it should be pretty self-explanatory. So the top, recall that we have 2 over square root of 4 minus t squared. And then on the bottom, we have 1 plus that guy. So 1 plus t squared plus 2t over no square root. This is just 4 minus t squared. 4 minus t squared. All right, now we want to, as I said, multiply both the top and the bottom by 4 minus t squared. Now for this top, it may not be immediately obvious how this is going to interact with this, but as I said earlier, we can actually rewrite this in terms of the square root guy itself, right? This is just, if we have a square root and then square it on the outside, well, the square and the square root are going to cancel and give you what we have back originally. But now we see we have the square root to work with, right? Okay, close that. And yeah, this is all like algebra 2 stuff, but no harm to going over it again. So arctangent. All right. On top, let's do some canceling now. So you see there's 2 of these guys multiplying, and there's one of those guys in the bottom. So if we have 2 on top, 1 in the bottom, then one of them in the bottom is going to cancel out with one of them in the top. So there's only going to be 1 left. So that's just 1 time, this thing to the power of 1, right? In the bottom, distribute this guy in. 4 minus t squared times 1 is just 4 minus t squared. And then plus the second term, this guy, and this guy completely cancel. So you're just left with a t squared plus 2t. Okay, and now you see that this guy right here and this guy right here are going to cancel. And yeah, we also can make one last simplification, and that is the common factor. Because if you notice, in the top, we have this 2, right, times this square root guy. In the bottom, we can factor out of 2 from both of these terms. So we factoring out of 2, that gets us on the inside. Factoring out of 2 from a 4 gives you a 2. Factoring out of 2 from this 2t just gives you plus t. So this 2 and that 2 cancel, and you're left with this guy's still going to be out here. It's been waiting here for a while. And then on the inside, you just have square root of 4 minus t squared all over 2 plus t. Okay, so that is the form that we're going to be working with. So I'm going to erase everything and put this guy up here and then see what we can do from there. Okay, so this is as simple as it gets. Even though it looks like you can do stuff with the inside and the outside of the inverse tangent, you really can't, because this in here is the argument of the function. Can't really do much with that. So now what? We differentiated this guy pretty successfully, and that gave us this. Well, now remember the original goal was to find a different form for I of t. So now let's go back to I of t, right? And how do we do that? Well, if this is the derivative of I of t, then we got to integrate both sides to with respect to I of t. Sorry, with respect to t. Because differentiating and integrating their inverses. So let's integrate both sides, right? Put an integral bar on both sides. So I'm going to move this I of t up into the top, because this is also pretty standard notation. Yeah. Okay, and I'm just going to copy this down. Okay, can't really integrate this quite yet because we're missing something. If we go ahead and multiply dt on both sides, then here it's just going to cancel, right? And then here it's going to pop out. So now, the left side we're integrating with respect to I of t, right? And the right-hand side we're integrating with respect to t. So we'll keep this guy here for now, and then let's work on this first, right? Because we want everything to pop out at the end with the satisfying snap. Okay. On the right-hand side, what do we do? This looks pretty complex to integrate, right? But what if we make a trig substitution? Because notice that we have inside of a square root a difference of squares, right? 4 minus t squared. And here, because the t squared is being subtracted, we're going to use a sine or a cosine. In this case, I'm going to be using just sine, right? That's pretty default. So let t equal to something that looks like sine theta. Now, one small thing is that right here, notice that we have a 4 here, right? If it was 1 minus sine squared theta, right? That's just what t is. Then that would give us cosine squared, which will cancel with the square root. But if it's 4 minus something sine squared theta, right? That's not going to cancel out. So we need to have a coefficient here. And that's just going to be the square root of this guy. The square root of this guy, right? They're the same expression. So this is 2. And you'll see how this works out for us in a second if you haven't already learned trig substitution. Okay, next we just got to find what dt is, because, we can't integrate something with theta in terms of t. We got to write our differential in terms of d theta. So how do we do that? Just implicitly differentiate both sides, right? On the left-hand side, you get tt. The right-hand side, differentiating this guy right here. The 2 is going to stay on the outside because it is just a constant factor. And then differentiating sine theta gives you cosine theta. And then differentiating theta using chain rule gives you d theta. All right, pretty cool. So now what? Plug everything in, right? So on the right-hand side, I'm going to move over here to do this, actually. We're going to be finding the antiderivative of this guy. except now we replace the t's with our trig subs, right? So first of all, we have this 4 minus t squared. Now what is t squared? That's just this guy squared, right? And that's just 4 sine squared. So let's replace this with 4 sine squared theta. And I think I'm gonna run out of room. Maybe, maybe not. Okay, inverse tangent. Okay, and then on the inside right here, we have square root of 4 minus t squared, and just the same thing as this right here, right? Earlier we saw that the square root of 4 minus t squared, that's just this thing, so we can just write that down at the top again. Square root of 4 minus 4 sine squared theta, and it's over 2 plus t, and t once again is just 2 sine theta. Okay, and then our differential, which is 2 cosine theta d theta. So 2 cosine theta, 2 is just the constant factor. I'm going to move that. Well, actually, no. 2 cosine theta is just multiplying onto everything, basically, right? So instead of writing it down here, I'm going to write it in the top of this fraction, because this fraction is also multiplying with everything. So 2 cosine theta, and then d theta, I'm going to write back here. And that was for the sake of room, right? Because otherwise we're going to run out of room. Okay, so this is important, right? I'm going to keep this here because later we're going to be going back to the t world. But for now, we got to find more ways to simplify this. So first of all, up top here, notice that this is just 4 cosine theta. Pretty simple, not much to think about. Okay, in the bottom, if you factor out a 4 on the inside right here, that gives you the square root of 4 times 1 minus sine squared theta, right? Because this term and that term, they both have a constant factor of 4. I'm moving that outside. Split up the square root. So square root of 4 is just 2. And then square root of 1 minus sine squared. Well, 1 minus sine squared is just cosine squared. The square root of cosine squared is just cosine. So this guy right here is really just 2 cosine theta. And we see that this is something over another thing. This cosine is going to cancel out with that cosine. And then this 4 over 2 is going to cancel to become just 2. So this whole thing on the outside right here is just going to become a 2, which we can even move outside. So basically this guy disappears. It just becomes a 2 that's sitting outside here. Next we have this arctangent guy. So we have the arctangent of, well, earlier we saw that this guy right here, right? Or at least we thought this guy right here, from here, we just got 2 cosine theta. And here it's the same deal, right? This is the same exact expression. So therefore, it's also going to result eventually in us getting 2 cosine theta. So I'm going to plant that guy up here. And in the bottom, what if we factor out a 2 from both of these terms? That just gives us 2 times 1 plus sine theta. D theta. These 2's are going to cancel, right? Okay, so now look at what we're integrating. We're integrating the inverse tangent of cosine theta over 1 plus sine theta. Now, that looks pretty bad because, you know, we still have inverse tangent of trig functions. It seems kind of weird to do, but it actually is more simple than you'd expect. Let's rewrite the inside a little bit. Right, okay. So, it's just cosine theta over 1 plus sine theta. And I'm going to do this work over here. Because we don't want an additive denominator, right? We want an additive numerator. So let's go ahead and multiply this guy by its conjugate, 1 minus sine theta. Same up here, 1 minus sine theta. So on the top, we're going to be left with just cosine theta times 1 minus sine theta. Pretty simple. And on the bottom, this is just a difference of squares pattern. So 1 minus sine squared, which gives you cosine squared. And there's a cosine up top, and there's a cosine squared in the bottom. One of these guys on top is going to cancel with one of the guys in the bottom. So what are you left with? Well, on top, you still have the 1 minus sine theta. But in the bottom, you only have one of the cosine thetas left. So we're going to put that down. Okay. So, in fact, we can put it down like this already, but if you notice, we can split up the fraction and then rewrite this. But for now, I'm going to write it like this because this form is actually also going to be important to us later, not just the fully simplified form. Okay, well, see here, this becomes 1 over cosine minus sine over cosine, right? And that's just secant theta minus tangent theta. Cool. So another way of writing this guy right here is just inverse tangent, but with this guy in the middle, right? On the inside, because we saw that this guy is equal to that guy. So I'm going to write this down again. 2 times the antiderivative of the arctangent. But this time on the inside, we can just write down secant theta minus tangent theta. Okay, so I almost ran out of room. Okay, which one looks better to work with? Which one looks more clean? This one, right here, right? Now, this is still pretty scuffed up. Like, how would you approach this? Maybe with integration by parts. But if I graphed the inside right here for you, then you can see what it looks like. Okay, and if you notice, if you look at it, it kind of looks like a tangent function, right? It has the same shape. So you would expect that if we took the inverse tangent of that, it's going to look like linear, right? Inverse tangent of tangent actually gives us something like that shape. And if I show you the graph of that, it does, right? So how is that true, right? If this thing inside of this integral right here is really linear like that, then that means its integral is going to be something, squared, because this is just something to the first power. But how the hell do we get there, right? How do we get to the fact that this you can rewrite as a tangent function? And that's the next step to this. So I'm going to rewrite these guys up here. And also, 1 second, actually, because importantly, before I do that, integral of di of t is just I of t, right? Think about it. Integral of d anything, dx, just gives you x. So therefore, integral of di of t is just going to give you I of t. So in reality, I'm going to just go ahead and replace this guy with I of t. There we go. So we don't need this derivative anymore, right? We can just start with this and go to that. So I'm going to rewrite everything, and then I'll be back in a second and show you how exactly we get from this guy, or even this guy, to just a normal tangent function. Okay, so now we're going to try to look for why this guy is really just a linear function on the inside. And earlier I did write that the inside is just secant theta plus tangent theta, minus tangent theta, and that might look like a better form, but in actuality, when we're trying to get to this guy being equal to some tangent, this is actually a better form to start off with, right? Okay, so let's start. And this journey right here, seems very out of the blue, right? You can't just find this. It's very hard to find this by yourself, so just stick with me through it. I actually looked this up on the Math Stack Exchange. So from here, let's just work with what we're trying to find right now. 1 minus sine theta over cosine theta. Okay, now let's change the sine theta just a little bit, right? If you recall, sine of 2 times x is 2 sine x cosine x. So in fact, we can write that down here, except for one thing. This isn't 2x, right? This isn't 2 times anything. So let's make it like that. Let's make it 2 times something. To do that, we just first divide by 2 and then multiply by 2, right? Because see, this 2 and 2 cancel out to give you just a theta left, and that's what we had originally. But now we have this guy in terms of this form, so we can rewrite it as that. So 1 minus 2 sine of x, and in this case our x is just theta over 2, cosine of x, which is theta over 2. Okay, in the bottom, how about we do the same thing with the cosine, right? Because it's better to have all of our arguments being terms of the same function. So this cosine right here, we can rewrite as cosine of 2 times theta over 2, just like the sine right here. And now we need a cosine double angle, right? So I'm also going to write that out. Cosine of 2x is just cosine squared x minus sine squared x, like that. So let's also copy that down in the bottom. Cosine squared, also just like above, our x is just theta over 2, right? Cosine of 2 times x is that. So cosine squared of theta over 2 minus sine squared of theta over 2. Nice. So this doesn't look much better yet, but we do have some cool forms popping out in the bottom, and maybe even on top. Okay, well, if you recall, 1 is equal to cosine squared x plus sine squared x, right? But x can be anything. It could be y over 2, right? As long as they're the same, right? As long as they match. So instead of writing this guy as sine of cosine squared theta plus sine squared theta, because everything's already in terms of theta over 2, I'm going to write it as cosine squared theta over 2 plus sine squared theta over 2. So yeah, let's go ahead and do that. And I'm actually going to write down this minus 2 sine theta over 2 cosine theta over 2 in the middle right here, because it's better for the visualization of what's about to happen next. Okay, so there we go. These two red guys is just equal to this one we had earlier, and in the bottom we still have the same thing. And now it should be really obvious that you can now factor the top, right? The top is a perfect square trinomial. Pretty exciting. We just get cosine of theta over 2 minus sine of theta over 2. So there we go. So that's why we rewrote this using all of this garbage. It's because we now have it in a more usable form. And in fact, the bottom you can factor too, right? This is just difference of squares. So we can factor this guy into cosine of theta over 2 minus sine of theta over 2 times cosine of theta over 2 plus sine of theta over 2. Difference of squares formula, right? And now, here's the cool part. This is squared. One of these guys on top cancels with this guy on the bottom. Right. So, now, we just have on top one of these guys left, so just cosine of theta over 2 minus sine of theta over 2 to the first power, and then over in the bottom, we're left with this term on the right-hand side, cosine of theta over 2 plus sine of theta over 2. Okay, so we now have more symmetries to work with, right? There's a minus on top, there's a plus in the bottom. So now we can see that this is in a much more usable form. The first step, these first two steps just might have been not that obvious. Okay, but from here, we're almost in a tangent form, right? Because I'm going to move this to the right-hand side right here. If you notice that if you just went ahead and divided both the top and the bottom by cosine of theta over 2, then, I'm going to write this in right here. Okay, so on top, if you distribute this guy into this guy, they're going to cancel out, and you're going to be left with 1. And then, distributing to the second guy, sine of that over cosine of that. Sine over cosine is just tangent, so you just get minus tangent of theta over 2. Pretty cool. In the bottom, same idea, right? This cosine is going to cancel with that, so you're left with the 1. There's a plus this time, and then sine over cosine, that's just the tangent, and with a theta over 2 on the inside. All right, and finally now, here's also a little bit of a, hard to think of step. But if you recall, 1 is just tangent of pi over 4, right? So we can actually rewrite this guy. This one up here, we can rewrite as tangent of pi over 4 minus tangent of theta over 2 over, I'm going to keep this 1 as just a 1, but we can also rewrite this guy as tangent of theta over 2 times 1, because, that's just it gets us back to tangent of theta over 2. But once again, 1 is just tangent of pi over 4. So this is actually tangent of pi over 4 times tangent of theta over 2. Like that. So, this right here, if you recognize it, well, I'll just write it out for you guys again. This is the tangent angle subtraction formula. So if you have tangent of alpha minus beta, then this gives us tangent of alpha minus tangent of beta all over 1 plus tangent alpha tangent beta, like that. And in our case, our alpha is just pi over 4, and our beta is just theta over 2. So we can go from this form right here, which is what we have it in right now, up into this condensed form right here. So this guy is just tangent of alpha minus beta, and our alpha is pi over 4, and our beta is theta over 2. So there we go. There's a lot of shit in here that you wouldn't have been able to think of yourself, right? Like maybe this, and definitely maybe that, right? But at the very end of the day, we see that this guy right here, which we got from the inside of there, is equal to that. So that's why secant theta minus tangent theta looks like a tangent graph. It's because it is. It's a tangent graph, right? It's this exact tangent graph right here. What does this mean for us? It means we can plug this guy into where we had this 1 minus sine theta over cosine theta. And then the tangent right here and the inverse tangent, they're just going to cancel out. So let me go ahead and erase this and write that in. Okay, so let's copy this down again. This 2 is going to stay times the antiderivative of the inverse tangent. But then we saw that the inside right here is just equal to this, right? So this is just the inverse tangent of the tangent of pi over 4 minus t over 2. Sorry, theta over 2. That looks like a t, I'm sorry. D theta. And earlier, I actually erased this, but remember that t is equal to 2 sine theta, right? That's the trig sub that we had to make to get to this theta world from the t world. So this and that cancel, and this is exactly why our graph looked like just a bunch of linear lines. It's because this is literally just a linear equation, right? Like that. Perfect. And now we can just go ahead and take the antiderivative. So the 2 is going to stay on the outside. Actually, you know what? I'm going to distribute it in. So in here, 2 times pi over 4 is just pi over 2. And then 2 minus theta over 2 is just normal theta by itself. Even better, because now it's so much easier to integrate than this tangent shit we had before. The inverse tangent stuff. Okay, so here, integrating pi over 2 with respect to theta is just pi over 2 theta. And then integrating theta with respect to theta is just 1/2 theta squared by the power rule. And then don't forget to plus c, because we don't have bounds, right? Okay, now you may be thinking, remember how this came from an integral? Why didn't we write a plus c on the left-hand side? Well, it's because if we just have a constant being added on here, and we have a constant also added on the right-hand side, we can just go ahead and combine those two constants, and then, you know, so that's what I kind of did with this. This is just both of the constants that came from integrating both sides. So now, there's 2 things we got to do. Got to bring this theta back to the t world, and we got to find out what that constant is. But first, I want to focus on the theta. So, recall that theta and t are related by that, right? But now we have the theta by itself. So here, I got to do the same thing. Find the theta by itself. Okay. So, how do we do that? Divide both sides by t first. Sorry, divide both sides by 2 first. So we get t over 2 is equal to sine theta. And then to free the theta, we just got to take the inverse sine on both sides. So inverse sine of t over 2 just gives you theta. Pretty cool. Okay. So now you just plug in an inverse sine of t over 2 for whatever is a theta. But in fact, you can actually factor out the theta first. So, and actually an over 2 too. 2, right? Because there's a 1/2 here, there's an over 2 here, and there's also a theta in both. So on the left term right here, what's left? We factor out a theta over 2, you only have a pi. On the right-hand side, you factored a theta over 2, you have one more theta left, right? And then we still have this plus c. Okay, but we saw that theta is just inverse sine over of t over 2, right? So I'm going to write this over 2 as 1/2, and then this theta just becomes inverse sine of t over 2. Okay, then we multiply by pi minus the inverse sine of t over 2, right? That's just theta. Okay, so now what? This looks kind of unclean right now, right? But let's recall another identity, and that has to do with inverse sine and inverse cosine. Recall that the inverse cosine of x is just pi over 2 minus the arc sine of x, right? This right here is true. So why don't we use that for both of these? And in fact, we can also switch the order. If we just add inverse sine on both sides and then subtract inverse cosine, we also have this right here. Pi over 2 minus, adding inverse sine on both sides, the inverse sine pops up on the left-hand side, and then subtracting inverse cosine on both sides, inverse cosine disappears from the left-hand side and appears on the right-hand side. So we also have this guy right here. This is also true. Right? Okay, so why don't we plug this in? Because right now, both of these guys are in terms of inverse sine. Maybe it has a chance of looking better with this inverse cosine right here. So I'm going to move this up here so it's easier for me to write. But we have this 1/2. Inverse sine of t over 2 is just, well, pi over 2 minus the inverse cosine of t over 2. Like this. And on the inside right here, pi minus inverse sine. Well, kind of see that if you break this pi up into pi over 2 plus pi over 2, then this pi over 2 minus inverse sine becomes our inverse cosine. So all we have on the inside that's left is this pi over 2 up here. And then pi over 2 minus inverse sine of whatever is just cosine of whatever, inverse cosine of whatever. And that whatever is a t over 2. So we have that and then a plus c. So now this actually does look a lot better because notice that you can factor this guy, right? This is just sum and difference pattern, which gives us the the difference of squares pattern. So this 1/2 is going to stay out here. We have a minus b times a plus b. So it's just going to be these guys squared. So that's going to give you pi squared over 4. And then this inverse cosine of t over 2 is also going to be squared. So I'm going to just write that down. All right, there you go. So now we have that I of t is just this guy. All right, so I'm going to copy this back down up here, and then we're going to try and find the constant. Okay, so right here, I just wrote what we had already up here. Now, before I continue, I want to take a step back and take a look at what's going on, in the meta. So, originally, if you remember where we began, we saw that this function, I of negative 2, right, is just has something to do with what we're trying to find. It's this sum right here, which I'll highlight by underlining it in red. Okay, well, now we have a different form of I of t. And how did we get there? We differentiated the inside, integrated, and then integrated to get back to where we are, to get back to I of t, right? But now, you see, this is a lot more direct, right? If we just plug in a negative 2 here, it's kind of hard to calculate what this is. I mean, we did get to here, but we couldn't get to what the exact value is. But after rewriting it to get to this, we can now plug in negative 2 again. And then that will just get us an equivalent form for this number, which will help us solve for whatever's underlined in red there, which was our original goal. But here, we still have a plus c. You can't just plug in a negative 2 there and then find the number because, right, there's this ambiguity right here in this plus c. So how do we find it? And for this, there's a whole nother thing we have to do. Now, notice that you can't just plug in some random numbers and have the C pop out, right? If you plugged in 0, this guy right here, you don't have a definitive value, right? Even though here you do. If you plugged in maybe 1, that wouldn't work, right? So let's do some tomfoolery. Let's focus on the original function that we have right here, this integral. So maybe what we could do is plug in some random numbers that seem to work nicely and then figure out if we can work out a relationship from there. So maybe plug in 0, right? Because 0 makes this whole center term disappear and that dumbs it down to just 2 terms. So observe that I of 0 is just the integral from 0 to infinity of the natural log of 1 plus, and this middle guy disappears. So it's e to the negative 2x. Well, hey, that almost looks like what we got earlier, right? Except there's a positive here, and there's this 2x up top instead of an x. But we can change that pretty easily. Not the positive, but the 2x we certainly can, because we can make a substitution. Let u go equal to 2x. Differentiating both sides here, du is just 2 dx. And therefore, 1/2 du is just dx, right? And also plugging in bounds. This is in terms of x. We're trying to find it in terms of u. So if x is equal to 0, well, u is 2 times 0. U is just 0, right? So once again, we're going from 0. And then top bound, 2 times infinity is just still infinity, right? So u is equal to infinity when x is equal to infinity. So the bounds don't change, but the inside right here, you get the natural log of 1 plus e to the negative, but we set 2x to be equal to u. Sorry if this looks kind of really ugly, but whatever. We saw that dx is 1/2 du. 1/2 I'm going to move up front since it's just multiplicative, like that. Now, let me remind you that u is just a name, right? This right here, what it really represents is some random graph, and that's whatever's in here, but that doesn't matter because what's going on is just this is the area underneath this line right here, right? Under this axis. So right now we're working on the u axis, right? From u is equal to 0 to u is equal to infinity. So it's just this area right here, which eventually converges, hopefully. Okay, well, does it matter? Well, the area still stay the same. If we just called this x instead of u, it's still going to stay the same, right? So what that translates to up here is that instead of calling it e to the negative u du, we can just call it x, right? So here's what's that going to look like. Going from x is equal to 0 to x is equal to infinity of natural log of 1 plus e to the negative x dx, right? This has nothing to do with what's going on over here. We're just renaming this guy right here, right? So in actuality, we can just ignore everything that's happened so far, right? All we know is that this value is equal to that value because it doesn't matter whether you call it the x-axis or the u-axis. The area is going to stay the same. Okay, so long explanation, but where did we really get to? We found that I of 0 is equal to this guy right here. Now, let's try something else in a second, though. I'm going to copy this up here, and then we can keep testing more numbers to see if we can find this constant up here. Okay, so we see that for this guy to factor nicely, we plugged in I of negative 2, right? But what if instead of a minus sign here, we had a plus sign here? It would still factor pretty well. So what would that be in terms of I of t? That would just be I of 2, right? Because plugging a 2 here would let it factor nicely. So let's try I of 2. And eventually maybe we can come up with a functional equation. All right, so I of 2. Integral from 0 to infinity of the natural log of 1. This time instead of minus 2, it's plus 2 because this t is just replaced with the 2. 1 plus 2 e to the negative x plus e to the negative 2x dx. Okay, and then now the argument of the natural log is going to factor real nice into 1 plus e to the negative x instead of 1 minus e to the negative x like it did earlier. So you can kind of see where we're going with this, right? It's because once we take this power down, this guy is actually, this integral part at least, is actually in the exact same form as this up here. So just watch it happen. 2, bring it down to the side. We get 2 times this integral from 0 to infinity of the natural log of 1 plus e to the negative x dx. That's just I of 2. So I'm going to go ahead and rewrite that back in, and then we'll see if we can compare the numbers to find the c that we've been looking for this whole time. Okay, so now this already looks really promising. Why? It's because these integrals are of the same form. So you can conclude that if you multiply this guy, I of 0, by 4, you could get to here, right? If, and I'm going to write this out, 4 times I of 0, well, that would be the same effect as multiplying 4 by the right-hand side. 4 times 1/2 is just 2. And then the integral is still going to stay the same. So let me just copy that down. Okay, but, and here is the connection. This right here on the right-hand side, that's just I of 2, right? See, right-hand side's the exact same. So in actuality, we have a relationship here. 4 times I of 0 is simply I of 2. And why is this helpful to us again? Like, it might look nice, right? It might look nice, but why exactly is this helpful? It's because I of t isn't just what's going on over here, right? I of t is also what's happening on the right side. So we can, instead of just using this left-hand side definition, we can now apply this relationship, which we found to be true, to the right-hand side, right? And then from there, we can calculate c. So how do we do that? Just write it out, right? So we get 4 times I of 0. But this time I want to use this as our definition of I. So 4 times I of 0. Well, I of 0 would just be plugging in 0 here. So I'm going to copy everything down except replace the t with the 0. Okay. And then this 4 is actually, this 4 distributes onto this term, but it also distributes onto the c term, right? So plus 4c. And we see that this is equal to I of 2. So I of 2 is just this here, but we replace t with the 2. And then this time on the right hand side, the c is just going to be by itself because we're not multiplying it by anything. Okay, so now we can do a lot of simplification. Right here, I'm going to move this over to the left side of the board. 4 times 1/2, I'm just going to rewrite this whole thing as 2. And then also notice we can distribute this in, right? So 2 times pi squared over 4 is just pi squared over 2. Okay. But more importantly, what the hell is this? Inverse cosine of 0 over 2 is just inverse cosine of 0. And what is the inverse cosine of 0? Well, you're finding, that's just saying cosine of what gives you 0, right? Cosine represents the x value on the thing. So when it's equal to 0, you're going to be on the line x is equal to 0. So basically up here, because that's the only part of the domain that lies on inverse cosine. That's a pi over 2 turn up, right? So basically inverse cosine of 0 is just pi over 2, because that's where it lies on x is equal to 0. So this in here gives us pi over 2, right? Pi over 2 squared. Okay, but remember, we had this 2 multiplied on the outside. We're going to distribute that in. And we still have our 4c. Right-hand side. Okay. Right here, let's also distribute in this 1/2. So 1/2 times pi squared over 4 is just pi squared over 8. And then we have 1/2 times this right here. inverse cosine of 2 over 2. Let's just evaluate what's going on the inside. Inverse cosine of 2 over 2 is just inverse cosine of 1. And where is the x value on the unit circle equal to 1? It's at 0 radians, right? This right here is x is equal to 1. So inverse cosine of 1 is just 0. So this is 0 squared, and then plus c. Okay, so there's a lot of cancellations we can do here. First of all, this guy is just 0, right? So we can just completely ignore that. Right here, we see that this guy minus whatever, this is just minus 2 times pi squared over 4, which is minus pi squared over 2, right? So this pi squared over 2 cancels with this negative pi squared over 2. So what are we left with? Well, all we're left with is that 4c, which is the only thing that's left on the left-hand side, is equal to pi squared over 8 plus c. Now, we just gotta isolate the c, right? So subtract c on both sides, we get 3c is equal to pi squared over 8. And then divide both sides by 3, c is equal to pi squared over 24. Okay, there we go. Pi squared over 24, very similar to a very long video I did before of the Coxeter's and Ahmed's integral, but that's a different thing. C is pi squared over 4. I'm going to box this because this is actually really important to us because we're basically done now that we found C. So I'm going to get rid of all of this work from down here. But now, and I'm going to rewrite this function, right? Instead of a C there, we're going to write down a pi squared over 24. Okay. Magical clean board, except now C is equal to pi squared over 24. So that's what I'm going to put down here. Pi squared over 24. Beautiful. So now this is completely closed. We have I of t is equal to that, but another form of I of t is just that. Now all we need to do is plug in negative 2, right? I of negative 2 we saw was this guy earlier. So now we can have something being equal to that and solve for this underlying part. But really quickly, I still want to simplify this a little bit more before we get too far ahead. So let's do that. First of all, let's distribute in this 1/2, right? So pi squared over 1/2 times pi squared over 4 is just pi squared over 8. And then this 1/2 times this inverse cosine of t over 2 squared, it's just going to be that, right? And we have the plus pi squared over 24. Now, see this and that, they're like terms. We'll combine them. So we need to pull out a denominator of 24 here. And how do we do that? Multiply by 3 over 3. 3 pi squared over 24 plus pi squared over 24 is just 4 pi squared over 24. Which, well, I'm going to copy this down again. Which gives us pi squared over 6. So, I mean, the answer to this guy already popped out here, but we're still not done. So we're going to keep going, right? This really isn't what we're trying to find quite yet, because we still have everything else that's going on. So there we go. We just found a much simpler form of I of t that doesn't involve that. And honestly, to be fair, I should have just distributed this earlier, but I didn't. So now we've got that down. Whatever, it doesn't matter. So finally, we see that I of t is just this. So I'm going to write this in right here. I of t is pi squared over 6 minus 1/2 times the arc cosine of t over 2 all squared. That's it. So now, finally, I of negative 2 is that thing, but we can also plug it into here. So if we just plug in t is equal to negative 2, well, earlier we saw it's just that, so I'm going to write that down again. Negative 2 times the sum going from n is equal to 1 to infinity of 1 over n squared. But we know I of t is equal to negative 2. We can also take that from this definition of I of t, which is pi squared over 6 minus 1/2 times the cosine inverse cosine of t over 2. But t, we're going to test t is equal to negative 2. So it's going to be negative 2 over 2. And this thing squared. Okay, so yeah. On the right-hand side, we can do a lot of simplification, right? Pi squared over 6 minus 1/2 times. I want to find out what inverse cosine of negative 2 over 2 is. Negative 2 over 2 is just negative 1. So once again, looking at the unit circle for the third time today, where is the x value negative 1? Right here at pi radians, right? So in here, this is actually just going to give us pi. Okay, now you have the square on the outside. Okay, so what is that? It's pi squared over 6 minus pi squared over 2. But for a common denominator of 6, multiply both the top and the bottom by 3. Pi squared minus 3 pi squared is just negative 2 pi squared over 6, which is negative pi squared over 3. Okay, so therefore, I of negative 2 is just, this thing is just that. So, therefore, this thing, negative 2 times the sum from n being equal to 1 to infinity of 1 over n squared is also equal to negative pi squared over 3. And we're almost done because all that's left is to divide both sides by negative 2. So, first of all, this negative on the left-hand side and this negative cancel out. Dividing both sides by 2, we finally have this guy isolated. And what is it? It's just the sum from n is equal to 1 to infinity of 1 over n squared over 2. And what is it equal to? Dividing both sides by 2. Pi squared over 2 over 3 divided by 2 is just pi squared over 6. Like that. And there we go. We found our answer a second way. This is pretty crazy. There's so many more proofs of this problem. This is just one that I found particularly entertaining because of how many elements we had to walk through, right? But yeah, it just happened to pop out of nowhere. We still found it. Pretty cool, right? Pretty cool.